So, last time we were discussing this result, which is the Equipartition Theorem. And I remind you that we came to this theorem from this identity. This identity which was saying that if you take any canonical variable xi and then take the partial derivative of the Hamiltonian with respect to another canonical variable xj, and then take the expected value on the canonical ensemble, then this is delta ij times kt. Okay, and one consequence of this is that if the Hamiltonian depends on the variable xi in a quadratic fashion, then when you take this derivative with respect to xi, you will have, let's say this is ai, so dh dxi will be equal to 2ai times xi. When you multiply by xi, you get xi squared, so you get the same part of the Hamiltonian which depends on xi multiplied by 2. Okay, so for any degree of freedom which enters into the Hamiltonian quadratically, this result implies that the average, the contribution of this degree of freedom to the Hamiltonian, to the energy, is equal to kT divided by 2. Okay, because when you compute this, you will have this is 2 times the average of ai times xi squared is equal to kt. No? So this is precisely the contribution of the degree of freedom xi to the Hamiltonian, and so this relation tells you that any degree of freedom which enters into the Hamiltonian quadratically will contribute to the energy by kT over 2 and to the specific heat by k over 2. Okay? Okay, so this is a result which is based on classical mechanics. So we have been using the canonical ensemble written in classical mechanics. So in order to understand the limitation of this result, when you go to so in particular this result will tell you so that the specific heat is constant even at low temperature, which is which, as we will see, is reasonable. And so, but in order to understand this, let's do a particular example. So we'll study a system of harmonic oscillators. Okay, and we take a very simple system, which is a system of n harmonic oscillators. And so the Hamiltonian of the position and coordinates is just the sum over, so let's say, I mean, these are also unidimensional, so for simplicity. Qy squared. Okay, so this is the Hamiltonian of As you see, these are n harmonic oscillators. They are identical and they do not interact. Okay, so we think this is a very, very simple stylized model of vibration in a solid. Okay, where this is very, very stylized model. So where we have solids, in a solid you have atoms which sit on regular positions and they fluctuate around their equilibrium positions. And in this model we also assume that they fluctuate completely independently. So an atom will oscillate around this position in a way which is completely independent of what the neighbors does. Okay, these are realistic. Okay, the pi squared and omega squared. I forgot a couple of squared. Thanks. Okay, but still it is an interesting reference system, so it's good to understand what is the statistical mechanics of this system and how we derive thermodynamics of this very simple system. So another but yeah. Okay, so what we have to do is to compute the partition function, right? Now the partition function is, we have written this in this form. Right? Now, however, in this case, if we think of this system as a system of, say, for example, a system of which describes the vibrations of the atoms around their positions, then in this case the particles are distinguishable, because each particle will be in a different position, right? Okay, so this implies that I should not consider this n factorial. Okay, because the particles will not move around. Okay, so there is no there will be, so the system will not visit a configuration where the particles interchange one with the other. Okay, so that you don't need to take to correct with 1 over n factorial. Okay. So what we have to do is to compute this the partition function for one single harmonic oscillator. And to do this, we have to do the integral of the momenta and the positions divided by h, and then there is the Hamiltonian, e to the minus p squared over 2m minus 1/2 m omega squared q squared. Okay, and this is a Gaussian integral. We have to integrate this from minus infinity to infinity, both in Q and in P. And okay, so strictly speaking, the positions should be integrated only within a volume. Okay, but since so these positions will be fluctuating over distances which are much less than the volume, then one can approximate this integral with taking the integral to infinity. Okay. So this is a very simple Gaussian integral that we have already seen. So if we do the integral in dp, so there is a factor square root 2 pi times divided by m. Sorry, there is also beta, no? There is also beta here, okay? So, when I do the integral in dp, what I have to do is to, so this will be 2 pi m divided by beta, because, yes, I have to, this will be the integral in dp, and the integral in dq will be 2 pi beta, no, sorry, divided by m omega quadro omega squared times beta. Okay, so m and m go away, and there is h, 1 over h. And so here you get 1 over beta times h bar omega. Okay? So the partition function for a system of n harmonic oscillators is beta h bar omega to the minus n. Okay? Now from this we can compute all of thermodynamics. So let's write it here. So, for example, well, then the Helmholtz free energy is minus kT times the log of this. So it's minus kT log of beta h bar omega. Well, I'm writing beta and as 1 over kT and kT at the same time. So, for convenience, okay? So beta should be interpreted as 1 over kT, okay? Okay, so for example now, and there is an n. So this tells you, for example, that the chemical potential is very simple. The chemical potential is the derivative of A with respect to n at V and T finite. And this is, sorry? This is a plus, yes. Yes. Thanks. There is the minus n, and then there is a minus, yes. Okay, indeed, I was getting a negative chemical potential, which was, so this is kT times the log of, yes, h bar omega over kT. So, well, and so the pressure also is very simple. How much is the pressure? What is the pressure? The derivative of A with respect to volume. So how much is it? 0. Okay. Pressure is 0 because, well, these particles are fixed in a position, and so they are not really confined in a box. Okay, so they are fixed to some position and they do not move. Yeah. The chemical potential? So the chemical potential is, well, we will discuss this next week, what is the significance of the chemical potential. But in general, if you think of a transformation where you change the number of particles, and we will discuss this next week, then the chemical potential is playing the same role of the temperature for heat transfer of heat, or the pressure for changes in volume. Okay, so there is a next week we are going to see that. So if you want, the chemical potential is how much, by this definition, is how much your free energy changes if you add one particle. Okay, so the contribution of one particle, if to the Helmholtz free energy. Okay, and next week we are going to see that this is an important quantity for when we consider exchanges, transformation where we allow systems to exchange a number of particles. Well, probably you have seen also this in thermodynamics, no? The chemical potential. Okay, so we're going to discuss this next week. Okay. Then we can compute the entropy. So the entropy is minus dA dt. And from this thing, there is a n k times the log of kt plus, well, then when I take the derivative of beta inside here, I get 1 over t. I just get a factor nk, so it's plus 1. Okay. So this is the entropy, and so you see this entropy is a problem. So if you plot this entropy as a function of temperature, so this you can also write it as kT times E divided by h bar omega. No? So this you can also write as n k times the log of kt times E, where this is Nepper's number, h bar omega. So which means that when kT is less than h bar omega divided by E, the entropy is negative. Okay, so this entropy, there will be a point here which is h bar omega divided by E, where this entropy will be go like the log, and then it will become negative. So negative entropy is not very nice, because we think of the entropy as being the logarithm of the number of microstates, which correspond to a macrostate. And the number of microstates should be an integer. So it should be at least 1. Okay? So the entropy should be positive. So the fact that the entropy is negative suggests that we are counting the microstate not correctly. Okay? And then what you can do is also to compute the energy. the energy of the system is, well, we can compute it by the relation, by this relation here. Now you see, if you take A plus T times S, then this term of A will exactly cancel this term here, okay? Because here you have exactly minus this term. And then the only thing which you have is nk times T, okay? And this is reassuring, because this is the Equipartition Theorem. We have 2 n degrees of freedoms, which are the P's and the Q. Each of them contribute kT over 2 to the Hamiltonian, so to the energy. So the total energy should be nkt, and it's okay. Okay. Very good. So the last thing which we can derive is the density of states. The density of states, the number of states which have energy E. And the way to derive this is to say well, one way is to do the inverse Laplace transform of the, because we know that this is so the partition function is the Laplace transform of the density of states. So the density of states is the inverse Laplace transform of the partition function. Okay, so you can do mathematically the Laplace transform. But the other way in which you can argue is by saying that well, the beta enters also only here into beta E, and then the energy here is positive, is always positive, so this will go from 0 to infinity, and you can make a change of variable into Z, which is beta times E. And so if you do this, you have 1 over beta times the integral from 0 to infinity dz of g of z divided by beta e to the minus z. And now you see that if you want to match the behavior of this integral with beta, then you have to assume that the g is proportional to g of e is proportional to e to the n minus 1. So you must have that this is proportional to e to the n minus 1. Okay, and then the integral which you are left with here is an integral which gives you a gamma function. So if you substitute, so this must be a constant times e to the n minus 1. So if you put this constant, then you have that this is 1 over beta to the n. times the integral from 0 to infinity in dz, z to the n minus 1 e to the minus z, right? And now you see this coefficient here. If you want to require that this coefficient here does not depend on n, well, it's just h bar omega divided by n. So then, sorry, and there is a constant here. Then you get that the constant there must be equal to, must be proportional to the gamma of n minus 1. The gamma of n, which is n minus 1 factorial. Okay. Or to 1 over the n minus 1 factorial. Okay. So this is the density of state. As you see, again, is a density of state which increases very, very fast with the energy. And so that this integral here is dominated always by the maximal value of the integrand. Okay. Okay. However, this problem, this classical result has problems because, as we discussed, the entropy is negative. Okay. And also, the specific heat is constant for all temperatures, so this is also not very reasonable. So let us see how does this picture changes when we consider a system of quantum harmonic oscillators. Okay. So for a system of quantum harmonic oscillators, the Hamiltonian is just the Hamiltonian of n independent harmonic oscillators. And each of them will have a discrete set of energy levels, okay? And these energy levels, so the energy levels of each of these oscillators will be, and will have energy n plus 1/2 h bar omega, okay? So again, we can compute the partition function as a function of beta, as the partition function of a single oscillator raised to the power n, because again these oscillators are going to be independent. Okay, so I can always factorize I can always factorize the computation of the partition function in the n in the different oscillators, right? So, and the partition function of a single harmonic oscillator will be just the sum from n going from 0 to infinity of e to the minus beta times the energy. Okay? And if I substitute this here, this is e to the minus 1/2 beta h bar omega. And then I have this sum from 0 to infinity, e to the minus n beta h bar omega. And this sum is just a geometric series. Okay? So I can compute it. This is e to the minus 1/2 beta h bar omega divided by 1 minus e to the minus beta h bar omega. Okay, so this is the partition function of one single oscillator, and so the partition function of n of them will be just this raised to the power n. So it's e to the minus 1/2 n beta h bar omega times 1 minus e to the minus beta h bar omega to the power minus n. Okay? Okay, and so again, and now again we can compute the Helmholtz free energy. This is minus 1 over beta times the log of Qn, which is 1/2 n h bar omega. This is just the log of this, minus 1 over beta, the log of 1 minus e to the minus beta h bar omega. Sorry, this is plus n. Okay? Right? Yeah. Very good. So now again, well, the chemical potential will be just this divided by n. So it's the pressure again would be 0 because so. But let us compute the entropy. The entropy is the interesting quantity which we want to compare. So it's minus the derivative of A with respect to t. So this term does not contribute. Here I have a term which is minus n times k times the log 1 minus e to the minus beta h bar omega. And then I have another term which comes from when I take the derivative inside here. So I have plus, I have minus n over beta, and then 1 minus e to the minus beta h bar omega. And then I have the derivative of this, which is, there is a minus here, and a minus here is e to the minus beta h bar omega. At the end, I have the derivative of beta with respect to t, which is 1. The derivative of beta with respect to t is 1 over beta is 1 over kt, so is 1 over k t squared. There is h bar omega, thanks, and there is a minus sign, right? It is raised to the minus beta. Yes, but I already took these two minus sign into account. Okay, so is a minus sign which comes from here. Okay, then this is 1 over this. Then there is the derivative of this, which is e to the minus beta h bar omega. Okay, and then there is a derivative of beta h bar omega, which is h bar omega kt squared. Okay. Okay. So in the end, so the result is that this is I can write it as nk. Let's write it as nk, and then So there is this factor here, e to the, well, this I can multiply by e to the beta h bar omega above and below. So this is e to the beta h bar omega minus 1. And then the factor which I have here is h bar omega divided by beta times kt divided by, so there is beta h bar, sorry, there is a beta h bar omega, okay? Beta h bar omega minus this term, the log of 1 minus e to the minus beta h bar omega. Okay? Yes. Now let's see how does this thing behaves for large temperature and for small temperatures. Okay. So for large temperatures, large temperature means beta very, very small, or actually here large temperature means beta h bar omega much less than 1, which means that we are looking at temperatures which are much larger than h bar omega divided by k. Okay, so this is a scale of, we are looking at temperatures which are much larger than this. Okay, there is a k also here, sorry. Okay. So when this is very, very small, I can, well, I can expand, expand the exponential here, and what you see is that there will be, so the entropy will be, I mean, to the leading order. Here, when you make the expansion of e to the beta h bar omega will be 1 plus beta h bar omega minus 1 is just beta h bar omega below, which cancel this one. So the first term will be essentially 1 plus orders of beta h bar omega, and then I have minus the log of, and again here there is 1 minus beta h bar omega, so it will be the log of beta h bar omega plus orders of beta h bar omega. So you see, this is precisely the formula, the classical formula which we have derived above previously. Okay, so it was, so you see this is a formula, you can write it as nk times the log of kt divided by times E divided by h bar omega. Okay, so you see this is precisely, it is precisely the entropy which we have derived before, which becomes negative when the temperature is less than h bar omega divided by k times E. So the limit when you take very, very large temperatures coincides with the classical limit. Okay. Now let's look at what happens at the other limit when we take small temperatures. So this function for very high temperatures will be essentially very similar to this. Okay. Now, when we take very high temperatures, it means that beta h bar omega, very small temperature, means beta h bar omega is much bigger than 1. So the temperature is very small, is much less than h bar omega over k. And then you see that the entropy, so the entropy will be nk. So in this term, this beta h bar omega is very, very large. So this 1 is completely negligible with respect to this. So there is a beta h bar omega times e to the minus beta h bar omega. And also here you see that this e to the minus beta h bar omega is completely negligible with respect to the 1, so there is log of 1. So this is essentially the result. From this you see that this entropy goes to 0. St goes to 0, as it should. Okay. So the quantum entropy will go to 0, and will go to 0 very fast, as the temperature goes to 0, no? Because it will go to 0 as e to the minus h bar omega divided by kt. Okay, so it's very, very fast, and then it will go up. So you see that this suggests that the equipartition theorem will only be valid for very large temperature for quantum systems. So let's, in order to make this more precise, let's compute also the energy. So again, if we want to compute the energy, is A plus T times S. So there is 1/2 NH bar omega, which is always there. Then so again, there are this term and this term. If you take S and multiply it by T, then you have n divided by beta times minus this log, which will cancel exactly with this. And you are left only with nkt times this object, which is h bar omega divided by e to the beta h bar omega minus 1. Okay, so this is the energy. So you see so the energy, if you plot the energy as a function of temperature, so the classical result was just a straight line. Okay, so the energy classical was just nkt. Okay. This instead, well, you can see that if we consider again the limit of very large temperature, so very small beta h bar omega, then you expand the exponential here. So you will have that so for beta h bar omega very, very small, the energy of the quantum system will be approximately 1/2 n h bar omega plus n h bar omega divided by beta h bar omega plus higher order terms. So h bar omega cancel, and you have just n kT. Okay, so the quantum energy will be just here will be just n, which multiplies kT plus 1/2 h bar omega. Okay, so it will be slightly above, but by an amount which is really negligible with respect to kT. Okay, and so they will essentially coincide for high temperature. And but for low temperatures, you see that this goes to 0, whereas this formula, this will go to 0, also exponentially fast, very fast. But the energy will go to the 0-point energy of the quantum system, which is 1/2 n h bar omega. So the quantum energy will do something like this. Okay, and so which means that you see here that the region where the equipartition theorem holds is at high temperature. Okay. Again, you can see from this that so the slope of the energy as a function of temperature is 0 at 0 temperature. So the specific heat will go to 0 at 0 temperature, and this is because also the entropy goes to 0. So since the entropy goes to 0, it means that there are no degrees of freedom which can be excited by thermal fluctuations, and so the specific heat goes to 0. Okay. So the last thing which I want to discuss with you is the density of states in this system. Now, in order to compute the density of states, we do the same trick as the other in the other cases. So so we know that this Qn of beta should be the integral over the density of states of e to the minus beta e. Okay, so we have this explicit expression here. So we want to put this expression in that form. So we want to put this expression in the form of an integral over the density of states of e to the minus beta e. Actually, since we have a quantum system, this will not be an integral, it will be a sum, because the energy level will be discrete. So there will be some there will be a sum over some energy levels r of g of ER times e to the minus beta ER, and this will be the number of microstate of quantum states which corresponds to energy level ER. Okay. So in this case, intuitively, it is clear that we have large n, big N of this harmonic oscillators. So we have to look for the number of ways in which the sum of n of these energies, in which I can have energy levels of this type such that the sum of the energy is equal to ER. Okay. But this is actually, I can derive this exactly from this formula. As so, what I can do is to use again the expansion of. I can write this as 1 over 2n beta h bar omega. And then this is just 1 over e to the minus e to the beta omega, which is just the sum from n equal to 0 to infinity v to the minus n beta h bar omega to the power n. And now I can use the multinomial expansion of this. And this will be e to the minus 1/2 n beta h bar omega times so I have a sum to the power n. So the multinomial expansion tells me that this will be each of these terms here will occur a certain number of times. So let me call it R and n, the number of times in which I will pick this factor here. Okay, so and I have to sum over all these integers. All the integers Rn larger than 0, such that the sum over the n of the Rn is equal to n, right? And then I have the multinomial coefficient. And then I have all these terms here, okay? I have, which is the product of this term, which is just e to the minus sum over n times Rn times beta h bar omega, okay? So what I've just done the multinomial expansion of this thing. Now you see, this is already in the form of a sum over energy levels, because you see here I have e to the minus beta times something, and here I have e to the minus beta times something. So you see that if I define this so this is clearly in the form of sum over all these set of integers of n factorial over product over n Rn factorial of e to the minus beta times 1/2 n n. Well, yes, 1/2 n plus sum over n times Rn h bar omega. Okay. Now I can make this sum a lot simpler, because so my energy level will be of only of this form. So 1/2 n plus an integer times h bar omega. Okay, so I can call this. So if I call this, if I call this number R, so my energy levels E of R will be equal to 1/2 n plus R times h bar omega. So this will be my energy levels. Okay. And how many times? So and this sum for all the Rn. So and the G of this. The number of times I will have this energy will be the sum over all the ways in which I can have these integers such that their sum is equal to n, and the sum of n Rn is equal to R. Okay, so this is equal to the sum of all the Rn such that the sum over n of Rn is equal to n, the sum over n of Rn times n is equal to R. And then I have the multinomial coefficient, which tells me that of all these ways of choosing these numbers, I should not distinguish, I should count them in this way. So if you think about this problem, this is exactly the problem of distributing, counting the number of ways in which you can distribute these many balls in these many boxes. Where, however, you don't. So because why? So because where the boxes are distinguishable, but the balls are not distinguishable. Okay, so why? Because say for any different choice of these occupation numbers of how many balls you put in the box, so you have this coefficient which tells you that for these occupation numbers you can distribute the balls among different boxes, but you should not consider different permutations of the balls where you exchange balls within the same box. Okay. So this means that the balls are indistinguishable. Okay. And then you have to sum over all the possible occupation numbers which are consistent with this. There was a question? No. Then you have to sum over all the possible occupation numbers consistent with this. So now this is a problem which can be solved with a simple trick, and the idea is that if you want to compute the number of ways in which you can put n r indistinguishable balls in n boxes, then the first thing is you start with start drawing one possible arrangement of this type. So these are your boxes, and then you have to put the balls inside. Okay, so this will be a particular configuration. Okay, now you see any configuration of this type which you can draw is so will be a sequence of balls and sticks. Okay, so I can so this will be a configuration which is like this. Okay, So where I have so I can remove, if I remove this wall here, which will always be there, and this wall here. So you see that any sequence of balls and sticks, when there are r balls and n minus 1 sticks, will correspond to exactly one of the ways to put these many indistinguishable balls in n boxes. Okay? And now it is clear that the number of ways in which you can, the number of different configuration of n minus 1 sticks and r balls, the number of possible ways, is exactly n minus 1 plus r, choose r. Okay, so this is the number of ways in which you have r balls, n minus 1 sticks, and the total number of objects which you have is n minus 1 plus r, and the number of ways in which you can combine these objects is this one. Okay. Very good. So so this is the expression of the density of state in the quantum system. Okay, so as an exercise, you can verify that when you, so of course, you see one thing which we should verify is that now we can consider the system in the microcanonical ensemble. And in the microcanonical ensemble, we would have so in the microcanonical ensemble, this system would have an entropy which is function of the energy, number of particles, and volume, which is the log, is k times the log of g of E. Okay? So it's k times the log of n plus r minus 1 divided by r, where r is where the relation between where the energy is 1/2 n plus r times h bar omega. Okay. Now, as an exercise, you can prove that the entropy which you compute in the microcanonical ensemble coincides with the entropy which you compute in the canonical ensemble. Okay? In order to do this, what you have to do is to, of course, in the canonical ensemble, you compute the entropy as a function of the temperature. Okay? So here you have the entropy as a function of the energy. So you should compute the temperature in the microcanonical ensemble by 1 over T ds dE. No? So take the derivative here with respect to the energy. Of course, you should use Stirling approximation for this. So you should use, by Stirling approximation, this will be essentially log n plus r. And also you can approximate n plus r minus 1 with n plus r. So the Okay, so this you can use this expression for the entropy. And then you compute the temperature, which is just ds dr dr dE. Okay, and then you verify that if you put then if you take this formula and substitute for R the expression of R as a function of T, you should get the entropy which we have computed previously. The same entropy which we have computed in the canonical ensemble. And this will tell you that these two descriptions, the canonical ensemble and the microcanonical ensemble, are completely equivalent. Okay? Very good. Okay, so there is another thing which I would like to discuss today, which is always, if there are no questions, are there questions? So by the way, next week you are going to do some exercise session, one on Monday, one on Thursday. And but you will be informed by Patrizia or Sandra. So I would like to go back to our result, which we have derived yesterday, which says that if we take, last time, if we take this expected value in the canonical ensemble, then we get delta ij times kt. Okay. Now, this relation is allows one to derive a result which is the analogous of the Virial Theorem. Well, the Virial Theorem is a theorem in classical mechanics, which tells you that the Virial theorem tells you that if you take a bounded system of particles, bounded system of particles means particles whose energy, whose momenta and coordinates cannot diverge. Then, if you take the time average of the kinetic energy, this means time average over a very, very long trajectory, then this is equal to minus 1/2 the sum over all the particles of the time average of the force acting on the kth particles times the position of the kth particle. Okay? This is again a time average. Okay? Now this is rather, well, you have studied the Virial Theorem, right? You know this. You know the Virial Theorem. So this is a very important result in classical mechanics, because essentially, for example, if you know, so one consequence of this is that so if the force acting on a particle is so if you have a system of particles which interact with a pairwise potential, and so you know the force which acts on a particle K is minus the sum over all the other particles of the derivative of the potential with respect to R K, and the potential will typically depend on R K minus R J. So, yes, okay, so you can take it also central potential, so that depends only on the modulus of the distance, okay? But in general, you can also think, may also depend on, in general, on the distance, okay, or on the, okay, so if you have forces which derive from this potential, and if you have a central potential which depends only on the distance, and in particular if you have a potential which only depends on the distance as a constant times the distance to the n, then what you can do is essentially you can rearrange this this term here, and in a way which is essentially equal to minus n over 2 times the expected value of the potential energy, okay? And the argument yeah, so this is not particularly complicated. So, but the main point is that this Virial theorem tells you that if you are able to measure, for example, the kinetic energy, then you know what the potential energy is, okay? And in particular, say for example, this is very much used in astrophysics, because maybe if you observe a part of the universe, maybe, or a galaxy, you are able to estimate the kinetic energy of light matter, of the matter which you can observe, and but if you know how much matter is there, you can also have an estimate of the potential energy, okay? So, and if the two things do not match, if the kinetic energy is much larger than the potential energy, or is larger than the potential energy which you estimate, then this is an indication that there should be some other type of matter which you don't see. And so this is one of the indication for dark matter, no, in the universe. So there should be some other matter which is responsible for the kinetic energy. However, the point I want to make here is that this result, the Virial theorem, can also be derived as a consequence of this equation here. Why? Well, because as we have seen, the average So if instead of taking time average, we take averages over the canonical ensemble, okay, so a fixed temperature, okay, then what we have seen is that the average of the kinetic energy at for a system of n particles in 3 dimensions. So the average kinetic energy at temperature T is equal to 3nk divided by 2 by the Equipartition Theorem, right? So because the potential energy, non-relativistic potential kinetic energy is just the sum of the momenta squared. So each degree of freedom, each quadratic degrees of freedom just contribute half of kT. Okay. But
we are not including the rotation of degrees of freedom in the vibrational lighting, right?
no, we are not including. Yes, yes. We are no, we are considering point particles. Okay, so they have no internal degrees of freedom. Okay, so we will. I think we'll discuss that at some point. So the second thing is that if you apply this equation where you choose the xi to be some particular a given coordinate, spatial coordinate of one of your particles, then this will tell you that qi times dh dqi, dh dqi is minus pi dot, so this will tell you that minus qi p dot I, this is equal to kT. Okay, and now, so it is clear that you see this statement here. Now, this is exactly the position times the force acting on a particle. So it's exactly equal to this, so that if you take minus 1/2 sum over all the particles of the average force acting on a particle k, so this will be equal to minus 1/2 times the sum over all the coordinates of qi times pi dot, and by this equality here, this is equal to minus 3n kT divided by 2. Okay. So now, if you compare, these and these with, these are plus sign. Okay, so you see that we have shown that the average, the expected value at temperature T of the kinetic energy is exactly equal to the virial. Okay, so this is exactly equal to the Virial theorem. The difference is that here the time is a time average, whereas here the time is an average over the ensemble. Okay. So, but but so this Virial theorem is also so it's valid in classical mechanics, in statistical mechanics. And you can substitute to time averages over ensembles. Yep.
Big T is the time average over the ensemble?
This big T is temperature. This means, by this notation, I mean average over the ensemble, canonical ensemble at temperature T. Okay, so this is sorry. So this is so we have derived this equation by taking an average over the canonical ensemble at temperature T, right? So okay, so let's do an application of these to ideal gas, of the Virial theorem to ideal gas. So so if we take an ideal gas in a box of volume V, then so if the gas is ideal, then the force which acts on the particles, I mean the particles are independent, so they are non-interacting. Okay, so the only force which they experience is the one when they bounce on the walls. Okay. So the only force which they experience is essentially given by the pressure. Okay, so this part of the equation in order to compute this part of the equation, you have to take an integral over all the surface of the system, because that is where and then the force which the particles will experience per unit area is just minus the pressure. And of course this force will be so the minus sign is because so this ds the normal to the surface will be going outside, but the force is going inside. So the force is this, and then I should multiply the ds times r. Okay, and I should integrate over all the surface. Okay, so this is my expression for this term here. And and now I can use the Gauss theorem to turn this integral over the surface into an integral over the volume. And what I should have is well, minus p, which is constant. I could also take it out. And then I have the divergence of R. Now the divergence of R is equal to 3. Is the derivative of x of R with respect to x of so. And so this is equal to minus 3 times the pressure, and then I'm left with an integral over the whole volume, which is minus the volume. Okay? So you see, this is this part of the this part of the equation. Then the other part, so the other part, the kinetic energy is equal to the energy for the gas, for the ideal gas. And we know that this is 3/2 nkt. So the Virial Theorem will tell you that 3/2 nkt is equal to minus 1/2 of that, which is 3/2 times PV. So you see that again you get the ideal gas law. Okay, so it's if you want, you get the ideal gas law as a consequence of the Virial theorem. Okay. So in the book you will see also how you can generalize. So what happens when you generalize this to a real gas? And in a real gas, what happens is that in this part, there will not only be a contribution which comes from the surface, but there will be also a contribution which comes from the interaction potential between the particles. Okay, and this is a volume contribution. So there will be another term which you have to add here. So this other term is not particularly difficult to compute, but just let me give you the result. So the result is that you can write the equation of state in the form in this form, which is minus 2 pi n over 3 times an integral dr from 0 to infinity r cube d u dr times g of r, where so this is a general equation which is valid for all the gases. So this is the potential between the particles. It is a central potential which only depends on the distance between the particles. So this and typically this u of r will be of the form of a form like this. So it will have a repulsion part, an attractive part, and then it will go to 0 at large distances. Okay. Now this g of r instead is the two-particle density, the two-particle correlation function. So is measure what is the probability to find two particles at a distance r. Okay. So indeed, so this quantity here is something which, if you know this quantity, then you can compute the equation of state. But this quantity is a quantity which depends on temperature. It will depend on temperature. It will depend on the density. So the difficult part is to compute for real gases what is the two-particle density. Okay. Okay.